Expressions and rational exponents. How are rational exponents related to radicals and roots? Well, they're both ways to express the same thing. A radical, you're kind of used to, that would be like the square root of 4. Well, we know that equals 2. A rational exponent, kind of new to you, that would be like 4 to the 1/2. And again, that equals 2. And we can try that in our calculator. The square root of 4 is 2, and 4 to the 1 control divide 2. You can see. So they're both ways to express the same thing. Remember that a number a is the nth root of a number b if a to the n equals b. As you know, a square root is indicated by the radical, and a cube root by the cube root. In general, the nth root of a real number a is indicated by a to the n, where n is the index. N is the index. So this n here is the index of the radical, and a here is called the radicand. Okay? Note that when a number has more than one real root, the radical sign indicates only the principal or positive root. Example, the square root of 4. Well, we know that 2 squared is 4, and we also know that negative 2 squared is 4. But by definition, we're just going to say the square root of 4 is 2. Now, that's a little bit different when we're working with like x equals. If you got x equals the square root of 4, you're looking for all possible solutions. So that would be x equals plus or minus 2. How can you express a square root using an exponent? That is, if the square root of a equals a to the m, what is m? Well, let's just use our math rules here. If you have the square root of a equals a to the m, we'll take the square of both sides. We'll square both sides, and that would give us a equals a to the mth squared. Well, m times 2, that's going to give you 2m. And that's called the power of a power property. Well, we know that this a is really a to the first power. Okay? And since we have the same base a, we can say that 1 equals 2m. Divide both sides by 2, and you get m equals 1/2. So the square root of a equals a to the 1/2 power. Well, does that apply more than just to the square root? Well, it applies to the cube root. The cube root of a equals a to the m. Again, let's cube both sides. Why the cube? Well, because we have a 3 here. A minute ago when we had the square, we just did squared both sides. But now that we have a 3 there, we're going to cube both sides. By the definition, a equals a to the m to the third power. 3 times m is a to the 3m power. Okay? Definition of a first power. Gives you a to the first, a to the 3m. Again, we have the same bases, and we've got 1 equals 3m. Divide both sides by 3 to isolate the m, and you got m equals 1/3. Pretty cool, huh? Discussion. Examine the reasonings in step A and B. Can you apply the same reasoning for any nth root? Sure. The nth root of A, where n is an explain. How can you do that? Well, we saw that the square root of A was A to the 1/2, right? And we saw the cube root of A was A to the 1/3. A to the 1/3. So by extension, the fifth root of A would be A to the 1/5. Also, the 10th root of A would be A to the 1/10. Again, by extension, the nth root of A would equal A to the 1/nth. For a positive number A, under what conditions on n will there be only one nth root? Two real nth roots explain. Well, let's see here. How do we explain that? For a positive number A, under what conditions will n will there only be one real nth root? Well, if n is odd, like 3, that's a little computer. Well, I got terrible handwriting. 3, 5, 7, and so on. You'll only get one real root. So if n is odd, the cube root of 27 is 3. The fifth root of 32 is 2. Now, so that's how we get 1. Now, what about 2 real nth roots? Well, that might happen if n is even, like 2, 4, 6, and so on. Example, you know that 2 squared is 4. Well, negative 2 squared is 4. So when you take the square root of 4, you get 2 answers. You get plus or minus 2. Now, like I mentioned earlier, if you're just taking the square root of 4, the principal root is 2. But if you had something like x equals the square root of 4, then you would want to all possible solutions. For a negative number A, under what conditions of n will there be no real roots? One real root, explain. Okay, that goes back to the odd and even thing again. Let's see, one real root. So if n is odd, like 3, 5, 7, and so on, and so you get the cube root of, say, negative 27. We know that is negative 3, because negative 3 times negative 3 times negative 3 equals 27. Negative 3 times negative 3, that's positive. Multiply that by negative 3, and you get 27. Negative 27. Negative 27. Negative 27. That would give you negative 27. Okay? Well, how would you get no real roots? How would you get no real n? If n is even, 2, 4, 6, and so on. What if you had the fourth root of negative 16? The fourth root of negative 16. What is that? That's 2i. 2i. Because because the square root of -1 equals I. We learned that in imaginary numbers. Translating between radical expressions and radical exponents. This is where rational exponents become very useful. They allow you to solve things easier. They're more convenient. I'll give you all something to read all that. And in A, you can read A. Stop the video for a few seconds and read it. Read that in A. What about B? Okay, now we're gonna move some stuff around. So we'll say A. All right, 81 to the 3 force power. So 81 to the 3 force. We're going to put the 4 out front and a 3 in the exponent. And the fourth root of 81 is 3. And the fourth root of 16 is 2. Well, 3 cubed. Remember, you got it all the way. Maybe we need to set out here. Let's do this out here. You've got 81 over 16 to the 3 force. Okay. And then we said that equals 81 over 16 to the fourth root of 16, and that's cubed. Okay. Remember, that becomes, what does that become? That becomes the fourth root of 81 over the fourth root of 16. And then we cube that. And we'll put that blue back to black there. All right, so the fourth root of 81, is 3, and the fourth root of 16 is 2, and then we cube that. And I'm just showing each step so you see where I get everything. You distribute that 3 inside, and you got 3 to the third power and 2 to the third power. 3 to the third power is 27, and 2 to the third power is 8. So we get 27 over 8. B. So we got xy to the 5/3 power. So what's going to come over here in this box here? What's going to come over here in this box here? What's going to come in that box there? The 3 is. And then the 5 is going to go in here. And 3. And then you can put the 5 out there as well. Either way, it gives you the same answer. And here's where radicals or rational exponents really come in handy. So we got the cube root of 11 to the 6th power. So that's going to become 11 to the 6 over 3. And 6 divided by 3 is 2. Well, 11 squared is 121. And how do we rewrite this? Well, that would be 2xy over the 5/3 to the 5/3 power. All right. How do you use a calculator to show that evaluating 0.001728 to the 4/3 power is the power of a root and is a root of a power are equivalent methods. Well, we can do that in our calculator. What was that? 0.001728, and then caret, and then four, control, divide, 3. Okay, good. Now let's take the cube root. And we'll 0.001728, and then we'll, okay. Well, I showed you another way as well. How about you open up the parentheses, and we'll take the cube root of 0.001728, and then we'll take that to the 4th power. Okay, it works. They all give you the same. Now let's play with a few of these. We're going to translate some. So we've got, well, let's rewrite this. Let's see, we've got, I don't know what happened there. Equals, and then we've got negative 32 over 243, and then what's our n going to be? Our n is going to be 5, and then we're going to square this. Okay, now what's the 5th root of 32? What's the 5th root of 32? That's going to be 2, and the 5th root of 243 is 3, and then we'll square that. And that's going to give us, well, negative 2 squared is 4, and then 3 squared is 9. Worked out pretty well. Not near as nasty as it looked, is it? So how can we rewrite this? Well, we can say this is the c root of 3y to the b power, which is the c root of 3y to the b power. Either way, isn't multiplication pretty cool? Now, here's another example where rational exponents come in pretty good. This is the cube root of 0.5 to the 9th power. So let's rewrite this as 0.5, and then we'll put the 9 over the 3. Well, 9 divided by 3 is what? Well, 9 divided by 3 is 3. So you got 0.5 to the 3rd power, which is 1.125. And then d, how can we rewrite d? We can rewrite it as st to the v over u power. Pretty cool. Modeling with power functions. The following functions all involve a given power, given power of a variable. A equals pi r squared. Volume, v equals 4/3 pi r cubed. And t equals 1.11 times L to the 1/2 power. That's the time in seconds for a pendulum of length L pendulum of length L feet to complete one back and forth swing. These are all examples of power functions. Power function has the form y equals ax to the b power, where a is a real number and b is a rational number. So we have a little biology problem here. The function r equals 73.3 to the fourth root of m cubed. That's known as Calvados Law. It relates the basic metabolic rate R in calories per day burned and the body mass of a mammal in kilograms. So a house cat has a body mass of 4.5, a cheetah of 55, and a lion of 170. Rewrite the formula with a rational exponent. Okay, they did that here on A, down here, because the nth root of a to the m equals a to the mn. The fourth root of m to the third equals m to the 3/4. So the formula is r equals 73.3 m to the 3/4 power. We're going to substitute 55 for m in the formula and use a calculator. The value of r for a cheetah to the nearest 50 calories. Well, we'll substitute 50 calories. We're going to substitute 55. Well, the 55, that's the weight of the cheetah, and they did that here. So you use that formula right there, 73.3 times 55 to the 3/4. So basically, it's 1,480 calories. And then C, from the table, the mass of a lion is about 38 times that of a house cat. Well, I think a lion had like 170 kilograms and a house cat is 4.5. If you put that in your calculator, it's going to be 78.8 or something like that. So we'll say it's approximately 38 times. Okay. So explain. Well, what you've got 73.3 times 170 to the 3/4, which is, this is what we did a minute ago, or I did a minute ago, 100 right over here, and it gave us 38. Well, the metabolic rate turns out to be about 15. So the metabolic rate for a lion is only about 15 times the house cat. The function hm equals 241 m to the 1/4 power. Models an animal's approximate resting heart rate h in beats per minute given its mass in kilograms. A common shrew has a mass of only about 0.01 kilograms. Well, how much is a kilogram? A kilogram is approximately 2.2 pounds. 2.2 pounds. So a common shrew, mass of about 0.01 kilograms to the nearest tenth. What is the model's estimate for the shrew's resting heart rate? So we're going to substitute 0.01 for m in the formula and use a calculator. So we'll put 0.01, 241 times 0.01 to the negative 1/4 is approximately 760. This model estimates the shrew's resting heart rate to be about 760 beats per minute. All right, B. What is the model's estimate for the resting heart rate of an American elk with a mass of 300 kilograms? So now we're going to substitute 300 for m in the formula, 300 for m, and that's going to give us about 60. The model estimates the elk's resting heart rate to be about 60 beats per minute. Find the ratio of the h of m for the larger animal to the smaller animal. Let one represent the mass of the smaller animal. So, okay, I can't do it on here, so we'll have to do it like this. Find the ratio of the larger animal to the smaller animal. Let one represent the smaller. Okay, so you have 241 times 10 and to the negative 1/4. Well, the 241s cancel out, so you got basically 10 over 1. 10 divided by 1 is just 10, so 10 to the 1/4, negative 1/4. That gives you 1 over 10 to the 1/4, which is approximately 0.56. You would expect the larger animal's resting heart rate to be about 56%. 56% of the smaller animals' resting heart rate. What is the difference between a power function and an exponential function? Well, let's see. A power function looks like this. You have some base, some unknown base to a power of like 5. And then an exponential function looks something like 2 to the x power. Okay? Where the variable is actually the exponent. So this right here, that's a power of a variable, and this is a variable of a power. So let's see here. In part B, so let me write something here for y'all. The power x to the 5th. So the base is, I don't want to do it in that color because you might get confused. So in a power function, the base is the variable, whereas in an exponential function, the variable or the exponent, the exponent is the variable. Well, I wonder what that looks like on a graph. Let's graph that. Let's try graphing that so we can get. So a power function would be like x caret 5. And what does that look like? Okay, so that is your power function. Your exponential function looks kind of different, and we would say that's we'll use 5 and then caret x, and then notice the difference. Whoa. Tab. Oh, don't do me that way. Tab. And then we've got 5 caret x. Not sure what happened just then. And notice the difference. So your x to the 5th, that's your power function. And then 5 to the x, that's your exponential. That's your exponential. So see how they graph kind of different. In part B, the exponent is negative. Are the results consistent with the meaning of a negative exponent that you learned for integers? Well, what did we learn for integers? We learned that, let's see here, x negative 2 power was 1 over x squared. Okay, what about for the rational ones? So if you have x and we'll say negative 2/3, that turned out to be 1 over x to the 2/3. So yes, they are consistent. Use Calvados Law from Part A. Find the basic metabolic rate for a 170 kilogram line to the nearest 50 calories. Then find the formula's prediction for a 70 kilogram human. I'll give y'all just a second. You can pause it. Calvados Law for a line. That would be 73.3. And a lion had 170 kilogram body mass, and that's the 3 force power. And that turns out to be approximately 3,450 calories. A little round in there. For humans, and we'll use a different color. For humans, that would be 73.3, and humans, 70 kilograms, 3 over 4, and that's approximately 1,750 calories. That's a little bit less than I usually take in on a day. Use your metabolic rate result for the line to find what basal metabolic rate for a 70 kilogram human would be if metabolic rate and mass were directly proportional. Compare the results from Part A. I'll give you just a little bit. Well, if they were directly proportional, what we have, that would be 3,450 for the line over his weight would be 170 kilograms. That would be, we'd say X calories. I'm not sure what's causing that, but I'd like to fix it. Calories. It did it again. X calories over, and humans, 70 kilograms. So let's see. You could cross multiply, and let's see. That would give you 170x equals 3450 times 70. 3450 times 70. And to solve for x, you would divide both sides by 170. So you got x equals, and let's see, 3450 times 70. I'm getting 241,500 over 170, which would be approximately 1,400 calories. So the rate for a human would be significantly lower than the actual prediction from Calvados Law. Explain how you can use a radical to write and evaluate a power of 4 to the 2.5 power. Explain how you can use a radical well, you could rewrite it as you've got 4 to the 2.5, 4 to the 2.5, 4 to the 2.5. You can rewrite it as a fraction, couldn't you? And if you rewrote it as a fraction, (2.5), that would be like 2.5. Wouldn't that be like 25 over 10? And let's see, 5 would go in there. It would be 5 and 2. That would be 5 and 2. So that would give you 4 to the 5 halves, which would be the square root of 4 to the 5th power, which would be 2 to the 5th power, which is 32. And to me, that would be a lot easier to do than that right there. That would be a lot easier to do than that. When y equals kx for some constant k, y varies directly as x. When y equals kx squared, y varies directly as the square of x. And when y equals k to the square root of x, y varies directly as the square root of x. How could you express the relationship y equals kx to the 3/5 for a constant k? Well, just following the other logic there, you would say that y varies directly as the 3/5 power of x. Y varies directly as the square of x. Okay. Essential question check-in. To evaluate the expression of the form a to the mnth power, first find the nth root of a, then raise the result to the nth power. To evaluate an expression of the form a to the mnth power, first find the nth power of a, then the nth root of the result. Which of the following are true? Both. Both are true. Okay. Sometimes it's more convenient to do it the first way, and sometimes it's more convenient to do it the second way. Whichever. It doesn't matter. It does not matter. Both will give you the same answer if you follow the pattern. And this concludes the lesson.